first time having a talk here, obviously. So I'm pretty thrilled. Let's see if it all goes well. I really hope so, and I hope you enjoy. Last year I was actually the first time in Athens, and it was the first time in Morocco, and it was the first time we can talk there, and I was talking about unicorns, the app servers, of course. This year, it's more about that bull there in the end. So actually in the movie there's a whole stampede of these bulls chasing unicorns. I don't know, anybody saw that movie? Yeah, so I'm not the only old guy here, it's 184. So don't worry, it's not really about movies here. Of course, it's about Rails and it's about cache stampedes. That's what I want to talk about. I just thought it was really funny that there is actually this movie poster where there's both the unicorns, which we still use as app servers, and the stampede in the background that's actually chasing them. So, give you a bit of context. So what we do as Confreaks is actually mobile advertisement. So we try to actually make it better than the funnels that you see all the time, that you just click accidentally. So we try to drive more app installs, basically. So we try to make you install even more games on your devices and play more stuff that you hopefully really like. And we're doing this with Rails. We were back then using Ruby 1.9, Rails 3.2, and MySQL 5.5. I don't actually know what the Memcache version is because that thing just works. That's kind of fully short, it never makes any trouble so far. So our admins know, but I'm happy to not really know. So from all these apps that are running, that are using our service, they come a lot of requests, and they will all reach the unicorns, the app servers where our Rails code is running. And they, of course, then toggle to MySQL, to Memcache, that's a pretty standard layout. And we went already through a couple of iterations of making sure that our queries are fine, that all the indexes are there that they need, that we're using the amount of caching that Rails is actually providing us, that we can actually use. Because the problem is we really want to optimize for the single user, for the single request, what we show there. Because in the end, if we just show everybody the same stuff, we probably just annoy a user, and they will leave the games, and nobody is happy. We're not happy, Captain probably not, and the game developer too, because you just stop playing this game, and that's bad. That's really not what we want to do. We actually want to show something that's interesting for you, so we want to optimize on the single request. That means that we cannot just use page caching, we cannot just show everybody the same stuff. We really want to do the optimization on the request. So everything that was or is being done, the tools that we have there is already used. And actually, back then, everything also looked pretty fine. So what is this? This is a graph of the CPU usage of our databases. That's a whole week. The green one is obviously the one that we use at the moment. The vertical lines are the deployments. So I guess there in the middle there was a weekend. Usually we deploy multiple times a day. And what you also see here is that the database usage never goes really above 50%, which is kind of really what we aim for, because we never know if some big application goes live and we will get a ton of requests. So we really would like to be able to handle this without having to call our the people that actually then have to set up these servers and stuff, and especially with database servers, it's really complicated because they're pretty big machines. So there is a lot of headroom here on purpose, and everything looked really nice, and we were busy writing more optimizations for algorithms that we use, not so much more performance algorithms. What we figured out over time is that when all of our graphs look like this and everything really looks good, it's usually just because we don't have enough graphs. There will be something somewhere that actually is about to break, because our traffic is always increasing, and so we hit new bottlenecks all the time. And actually that's exactly what happened here. After that, this is what happened. This is my top. If you're using MySQL, you probably know the tool. You don't have to really read all of that, but the sense here is it shows you all the queries that are running currently in your database. And if you use that tool, you know that this is not how it should look like. So there are multiple problems here. One is there are tons of queries. That's kind of okay. They're all the same. That's really not good. And what's way worse is they're all running already for a minute, or actually even more. And that's really bad. That's actually a moment where we are down and where the database load, of course, goes up to 100%, where the number of requests, like usually 50 to 100,000 per minute, goes down to nearly zero. And our product owners are not happy, or MySQL is not happy, and so I'm not really happy, and we have to figure out what's actually going on, and fast, because we're not earning any money, and all the people we're working with don't get the service that they deserve. So, but how could that happen? Because just a moment before, everything really looked cool, and our database was not even really busy. And I will try to explain this. This is, when you see it the first time, it's actually not so easy to understand. And I'm trying to depict the time here, so this is a timeline, and there are requests coming in, these little ticks above the line, and at the moment they're just coming every 100 milliseconds. The reality, of course, looks a bit more messy, but just for the sake of the argument here, they're coming every 100 milliseconds. And our database is at 20% load. That's really cool, everything nice. But then we start to get a bit more traffic. No, first we get the cache invalidation. So what we do is, we have a lot of dashboards where users and our own guys can actually change the data that we have in the database. And they can just update whatever the payout or the title or whatever else on that capacity. So whenever this happens, we have to invalidate the cache so that the users see new things. That means that the next request after the cache invalidation, we will start a query to new content of MySQL. And that's cool, happening all the time. So then the user, after that, actually will get again content from the cache. There's not a new content, so we don't need to do another query. Everything great. So now we get a bit more traffic. So now the request comes every 80 milliseconds, but for our database, nothing changed because, well, there's still only one query, so database load is actually the same situation as before. But if we get even more traffic, then something starts to happen. Well, now the request that comes after the one that starts the query still doesn't see the new value in the database, in the cache yet, because the query in the database is not done. So this request will actually trigger a new query, second one. And that's not really critical, but already you can see that probably in your graphs, because now you do two queries instead of one. So just for a bit more traffic, we actually get twice the amount of queries. And that, of course, is not great. But so far, because we have the headroom, actually nothing bad happened really good. But then, getting even slightly more traffic, there starts to be a really big problem. Because now, the first query that started becomes slower because there is a second one starting right in the middle of it. And because it becomes slower, it's actually not finished before the third query starts. And that kind of spirals down really quick into something that you cannot control anymore, and you will have as many queries in your database as you have connections. And because we have lots of traffic, so we have lots of unicorns, lots of web servers, and lots of connections to the database, we will have a couple of hundred of these queries in the database very soon. And at that point, it really looks like, it feels like there is nothing moving in the database anymore. Which of course is not true, it's really busy, it's at 100% CPU, but it doesn't help you anymore. You're doing, or you just make your database fully busy with the same query over and over and over again. So that's, of course, the thing that you would love to avoid. So, it's very unlikely that we are the first one to actually hit that problem. And in fact, active support seems to know that, and there's an option if you cache objects with RailsCache that's race condition ETL. don't try to read the fine print there. I will try to explain. The idea here is that the cache drawer is actually cheating a bit when telling Memcache how long the object should live. So it will not use your time to live that you give it. It will extend this period a bit, actually by the value that you give to the option based on TTL. And instead store the real time to live with the object in the cache. So when the time to live is over, you still get the value from Memcache, because Memcache thinks that it's actually valid for a longer time. And Rails will then start the query. But before doing so, put the old value back into the cache with a new time to live, so that all the other processes that also try to read from the cache will now still see the old value there, and will still serve the old stale content. And it's probably not perfect, but it's way better than going down because of all the queries. So that's a pretty neat option if you actually use the time to live for invalidating your caches. That's probably really the way you want to go. But as I said, we're only manually changing the data in our database, so we don't know when we will have to invalidate it later. So using time to live is for us not really an option, and so unfortunately we cannot really use this time to live or the race condition option. But of course, this is very, very helpful in certain situations. So the idea here is that you can turn load that is relative to the number of requests that you get every minute to the constant load. So, meaning before, actually, when you have no cache, you will do a query for every single request that comes to your servers. And now by just caching something for like 2 seconds, for example, you turn this into something that's constant. So you will only do one query every 2 seconds. Probably nobody will notice that the content is 2 seconds old, so that's a good idea here. But it only works, at least with such a short time span, when you have like an item in the cache that you really query very, very often, that you really query with every single request, or at least with a big amount of requests. So our items in the database, the things that we want to store in the cache, are pretty many. So we're doing this like for every single application in different countries, and so we actually get to a couple of thousands or even tens of thousands of objects that we store to the cache, and we cannot invalidate all of them just every 2 seconds, because that probably means that we will do tons of queries again in the database, because whenever somebody comes for this specific combination of application and country, the cache will be expired already. So that doesn't really help us. But well, let's look at what other kinds of strategies there are to actually invalidate your cache. First one, so I already talked about now. If you use time to live, don't forget to use the rest of the TTL, because it will save you from this situation we just saw. And there would be a really nice way of actually not invalidating the cache, but updating it whenever you also change data in the database. So the idea here is just whenever somebody writes to the data, he also writes to the cache. That works only if probably the application that writes data is the same that also reads it. Else, well, we have to have access to the same cache, which at least in our case is not the case. So we don't want to write to the cache from a different application than the one that reads from it, because then you get in all kinds of troubles if you upgrade your Ruby version, for example, marshaling changes the format, and then you have to update both applications at the same time, and else it will just crash. So we don't want to couple the writing application and the reading application so closely. But if this is the same application in your case, then it's probably a great idea to go. What we ended up is content versioning. So we're not inventing this. I heard the first time in the Shopify blog post, I think, of this. So the idea here is pretty simple. We store a version number with every item in the database that we also want to cache. Meaning whenever we change the data, we update that version number, and everybody who has a cache with that item in it has to check if the version of the cache is also the version of the current item. and if not, you have to update the limits in the cache. Then of course you need to store that version number somewhere, and I already said it, it will probably be in the database, because that's where the data is, and that's where everybody who writes data has access to. And that of course means then that we have to query the database again every time for the version number, which is not really the idea, because we just try to actually get the load away from the database. And these queries are pretty simple, of course. I mean, they only have to get one single integer out of it, so they are really fast. What we actually saw is that MySQL, at least on our hardware, there is kind of an upper limit to the number of requests it can do per second. Around 10,000, 11,000 or whatever, but that of course depends on your hardware per second. So I think it's really great. But with all the queries to those cache numbers, or to those version cache numbers, that didn't really work. So what we ended up is, we actually also put the version number into the cache, into Memcache. So now, with a really short time to live, meaning we will actually query the database every 2 seconds for the version number, put it into Memcache, and everybody can check the version number being Memcache, see if that's the one that also is available at the moment for the real object. If so, serve it. If not, well, we have to go to the database. So it all starts to be a bit complicated. But it works, and it actually works pretty nice. What we then figured out is that, well, we're getting more traffic, and our database is fine now. But our app servers start to consume really lots of CPUs, and we have to buy new servers all the time. And starting to profile and looking on what really the problem here is, we figured out it's two things. It's marshaling actually eats the CPU, so turning our Ruby objects into streams of data. That takes a lot of time and a lot of CPU. And the second problem that we see here is, well, the round trip times to Memcache start to pile up. Because now we're always going twice to Memcache, because we need the version number first, and then we need the object. And we're not only doing this for a single object with every request, but with a couple of them. So we need a lot of stuff to put in the cache. And they're pretty thick, and all of these times really start to add up. So the first problem is, as I said, marshaling, so serializing data. And so don't take these numbers too serious. That's not meant as a benchmark, but it kind of gives you an idea. So there are different ways, of course, of serializing your data. And the most obvious and the default one is just Ruby's Marshal. But of course, you can use YAML, you can use JSON. OK is actually just a different implementation of it. And then there's also message packets. And there are, of course, more, but these are the ones that we looked at. What you can see here is already the data produced by Marshal is actually the biggest. And then YAML, JSON are a bit smaller. Message packet is actually like 4 times smaller than Marshal. It depends a lot on the data that you put in, of course. So don't really trust these numbers. Check it with your own data. What I did here is just a hash or an array with 100 hashes, and every hash has 26 members with a random number. So if your data looks differently, try with different data. But for us, these numbers are kind of representative of what's going on with real life. And then on the bottom, there is the time that it takes to dump this data and to load it again 1,000 times. And the main takeaway here is, this is not what YAML was made for. The thing is 100 times slower than the message pack, so don't use that. Marshal actually is quite okay. Takes 4 seconds on that machine. And then JSON is actually pretty much the same. OJ is a really fast implementation of JSON. So if you're looking at JSON, which is kind of nice because then you can actually read what's in your cache. With Marshal, I mean, you will not really be able to see what's in there. Same is true for message pack. These are binary formats, and so you will not be able to read that. With JSON, of course, you have the benefit of just being able to walk directly into your Memcache and what's in there. But also here, message pack is 4 times faster than marshaling. So both the size and the speed argument is really in favor of message pack. And of course, I know that the comparison is not really fair because marshaling is actually doing a lot more things. You can put real Ruby objects in there, and you can expect them to get out of the marshaling process pretty much as they were before. Message pack is limited to the same set of types than JSON is. It's mainly just arrays and hashes of strings and integers. But if you have your data in this kind of format, then it's really worth thinking about if Marshall is the right tool here, or if maybe message pack would be better. The most stupid thing you can do, actually, and we did this, is put your version number in the cache as an object. So we just vary it in the database, have a data mapper object. There's actually only one value in there, and then we wrap that in a RailsCache item, and then we serialize it with Marshall, and we put it to the Memcache. Then that means that your single integer that you wanted to store is 20 kilobytes in size. I mean, that's so inefficient that you really think hard. There is a raw option for RailsCache, and that will actually make sure that it doesn't wrap your data into the cache item. So what you have to do is, when you get it back, you will get a string, so you have to call to on it, but that's really worth it because you just save 20 kilobytes in your Memcache for every single version number that you store. So it works pretty cool. And it's also pretty obvious where we ended up with. The other problem that I said is round trips. And again, we thought, so we cannot be the first to actually see this problem, so we had a look at what's there already. And there's a memory store, which I think is not really used very heavily. There's a reason for this. So the memory store, connected support, stores stuff locally in your local process memory. That's why it's called that way. But it does so by also serializing the data, so and then storing the string, and whenever you want to get it out of the cache again, it will deserialize it. So you have to pay the cost for the CPU cost for doing so every time. So that's not really optimal, especially if you're stored locally anyway. And on top of that, it falls back to the database. So now every single unicorn has its own copy of the data, and then when this is updated, it goes back to the database. And that means, we do 640 queries every time, because we have lots of servers, and we have lots of processes on these servers. Why are we doing this? Well, for the 32 processes per server are just there to make all our CPUs busy. There are like 16 cores on every machine. So if you really want them to be busy, you need a lot of processes. At least if you use MRI as we do, so you just need it. And then we have 20 servers just because we get all of this. So we don't want to have 640 queries because that's where we started with. We don't want to have the database full of the same queries all the time. So then we actually thought about, well, okay, then let's roll our own. And it turned out that's not really very hard. So what we want is we want to store really the objects locally, and we do so in a simple cache, in a Ruby cache. That's nice because the hash is actually ordered by insertion order. So with a pretty simple LRU, so least recently used algorithm, we can make sure that all the hot items in the cache actually stay in the cache, and all the old stuff drops out. So we have a plain old hash. Keys are the keys that you would normally use as keys in Memcache, and the values are just the objects you want to store. But not in a serialized format, but just simply the objects you wanted to cache. It's probably a good idea to freeze them so that nobody actually starts to change them. But when you do that, it means that whenever you want to access one of the hot of the really often used items on a cache, all that happens is that you have a single hash lookup to actually go to that object without any serialization whatsoever and without any routing whatsoever. So it really can't get hardly any faster as long as you use root at least. And there's another benefit because you're really using these objects all the time. You actually don't have to garbage collect them with the traditional method of just getting them out of Memcache. Means you get a string out of Memcache, you can then build up all the objects in memory by unmarshaling them, and then you have to get rid of them again also. So the garbage collector actually becomes very, very busy and was just cleaning up all that stuff that you produce here. So this is avoiding all of this. It's just already there, it's just in the format you need it. So it's really awesome and actually speeds up the request time quite a bit. And the only drawback that you have is that you store now a lot of the objects in the local memory. And because we have 32 of these processes per server, that also means that your servers probably need quite some memory, at least if you want to have a big local storage here. But we can configure the amount of items we want to keep in the cache, so we can actually tweak it so that we don't run out of space for memory on the servers. So everything cool and done? No, not really, because we still have the problem that whenever we invalidate something, all of those processes will look into their local cache, they will actually figure out, no, my local cache doesn't have the right version of the object. Then they will all go to Memcache, and Memcache also doesn't have the new object yet, because it was just invalidated. And then all of them will actually try again to go to the database, and we are still kind of tough. So then we had a look at this and decided, okay, we need a way to actually let them all communicate with each other and figure out that only one of them goes really to the database, and everybody else should wait for the new version of the cache to be available in Memcache. That would be enough already. If only one goes to the database, all the others will get the value kind of in the same time if they would just wait and retry in Memcache instead of going to the database and just crush it. So now you can of course have a lot of fancy inter-process communication, whatever, I mean, you can go really crazy there. But we thought, okay, they are already using Memcache and they're all already like communicating that way, so why not use Memcache to tell everybody to wait, except the one process that actually really has to go to the database. And that's what we built. So whenever there is not the right value in Memcache, what we do is we write a flag there, a unique value that just tells everybody else. So if you see that value, then please don't do the query and don't serve the user with an empty response. What you should do is just wait and retry. And that works amazingly well, especially because Memcache has a nice command for adding a value atomically, and only one of the processes will be successful of writing this value. And so Memcache will actually synchronize all of these processes, making sure that only one is able to write a flag to Memcache that everybody else should wait. So I call it the busy flag. One writes this, everybody else waits until there's a real value. And because that's actually helpful for us in a lot of situations, we wrap that up in Kröger. We will open the repository today so that everybody can have a look there. Somebody said you should not deploy stuff when you're still, when you're not embarrassed of doing so, or not embarrassed anymore. So we are kind of still a bit embarrassed about the code that we have there, so please deal with that. But it is really helpful. I mean, we're using it in production. It's actually on a heavy load, so I think it's really worth having a look. So So this, and there's a wrapper for it that makes it Rails.cache compatible, so you can really just put it, drop it into your project and use it, and then by default it will use marshaling, because that just allows you to use it the same way as a Rails.cache with putting objects in there. If you're in the situation that you already like store things just as caches and arrays, then probably you want to change the default to use message tag, because then you get the extra thing. So it falls back using DALI, so it falls just back to Memcache, and then of course that's not successful because of the database. So we'll back to our initial timeline. When we validate our cache, and the next request now does declare it to the database, and the request after that kind of finds an empty cache, it will not go and create another query, as it was the case before. It will just retry going to the cache after a couple of milliseconds, and then hopefully we'll find a new value there. Actually, not it will retry again, so that this query doesn't take any longer than it did before, because there's only one of it, and everybody will just get the nice new content. So, problem solved. We're, as I said, running this in production. Didn't have any of these cache storms where we got run over by a million queries anymore since then. You can have that too, at least if you see something like that happening on your production system. I actually really hope you will remember that, and it's a bit helpful that you saw that. And yeah, thank you.